and the distant galactic halo.
Can you guys all hear me? Back there? Okay, cool. So thanks for the introduction. My name is Sijie, and I go by Anna. I'm currently finishing my second year in UC Irvine. So today I'm going to talk about the work that I've been doing with my advisor, James Bullock, and also my collaborators, Andrew Wetzel, Robin Sanderson, Andrew Grouse, and also, of course, the whole FIRE group. So my work mainly focuses on the stellar halo of the Milky Way-like galaxy, especially the outer part. So briefly, here is the introduction. There are a lot of theoretical and observational work about this special part of the Milky Way-like galaxy. So observations have found a lot of substructures in the stellar halo, and the famous Bullock and Johnson model, they actually, by assuming an accreted-only formation scenario, they have successfully reproduced those substructures here. So the conventional thought about the formation of stellar halo is that the stellar halo is actually almost entirely built up from those accretion and disruption events. But recently, however, there are more and more people realize that there might be some contribution from the star, from the center of the galaxy too. And some people prefer to call them in situ stars. So my work actually very different from my advisor James, actually focused on this kind of special population in the stellar halo. So first of all, excuse me, I want to show you this video. So I've been using the latte simulation. As Andrew has already talked about it in his talk, so I'll just skip the introduction here. So this is a visualization of the star in one of the latte primary halo, M12I, which later forms into a Milky Way-like galaxy. As you may have already noticed in this video, that we actually see a lot of stars getting kicked out from the center of the galaxy. Like this, they're coming out from the very center of the galaxy. So I want to emphasize here that you are seeing the visualization of stars only, so it's not gas outflow. And it's very interesting because we know that in a simulation, stars cannot be pushed. It mainly reacts to the gravity of the galaxy. So what is happening here? Is there anything wrong with our simulation? So luckily here we found an observational paper that claimed that they detect star formation inside a galactic molecular outflows. And also, there are more recent papers actually pointing out that those star formations are actually really popular inside the outflows that they have observed. So in their model, stars formed inside those outflows with really high initial velocity and then are very rapidly decelerated because of the gravity of the galaxy and may even just fall back in after some time. So this sounds really similar to what we are seeing in our simulation. So is this what's happening there? So in order to test this, we actually need to see what is the gas behavior during the formation scenario. But because in a FIRE simulation or in a latte simulation, the output frequency is not high enough to see like what's exactly happening right there. So here, what we did is that we choose one event and rerun it with a much higher output frequency to see what's happening. So this video shows the events that happening in the rerun. So we actually spotted a similar event happening in about the same place and at about the same time. So we grabbed those star particles inside the stream and traced them back to find their apparent gas particle. So in the movie, we marked those gas particles with the magenta points, and those colorful points are the stars that formed inside that outflow, and they're color-coded by their star formation time. So here we can see the gas cloud, they got compressed and then formed star, but it's still not enough. So what we did here is that we plot the average velocity for the gas particle and star particle separately as a function of time. So here, very clearly, we see that the gas particle, right before they turn into stars, they get accelerated. And the star particle formed with a really high initial velocity. So from here, at this moment, I think the picture is kind of clear now. So some feedback events in the fire or lattice simulation happens to accelerate a large, dense gas cloud, and then star forms inside that gas cloud with a really high initial velocity, and then because of the gravity of the galaxy, they got decelerated really fast. And after some times, we're not seeing it here, but it's possible that they might fall back in and contribute to the galaxy, and very likely to the outer stellar halo. So this is very preliminary results we got. So now if you believe this is true, then what are the properties of those stars? How are they different from those, for example, accreted stuff? So our next step here is to try to look for their properties. So as you can see in this video, those kicked out stars, they were born in the very center of the galaxy. So here what we did is actually really, really simple. So we just select those stars with burst radius less than 10 kpc to be the kicked out population. So the burst radius is the distance from the star to the center when they formed. So stars with such a short burst radius, it's very, very likely that they are born inside a galaxy. So some people prefer to call it in situ. So here, just to be clear, that these four terms in my following talks, they basically mean the same. So first of all, we're trying to quantify their contribution to the outer stellar halo. So here we show the density plot for other stars and the kicked out stars here. And by calculating the ratio of these two density at different radius, we get a fraction as a function of radius. And we apply this to all the other simulations that we are looking at. We got this one plot. So surprisingly, we actually see the fraction is actually pretty high. And it can even reach like 20, 30, or even 40% at certain radius. And even when we calculate the total fraction for other star outside, say, 20 kiloparsec, most of them are higher than 10% actually. So then let's look at the phase space and spatial distribution. So in the top two panel, we show the radial velocity as a function of present radius for the two populations for the kicked out stars that is born within 10 kiloparsec, and the stars born outside 200 kiloparsec. So the stars with such a large burst radius, they must have been accreted from other systems. And they're color-coded by the star formation time, which is equivalent to their ages. And the lower panel, we show the face-on projection of the spatial distribution for the same two populations and color-code by the metallicity. So compared with the accreted stuff that has a lot of substructures, we actually see that the kicked out stars are more evenly distributed, and we see no obvious clumpiness or substructures here. So I don't know if you have noticed it, but in the bottom panel, we actually see a color difference, which means their chemical abundances is also very different. So our next step is try to see their chemical abundances differences. So here we show a kernel density estimate plot for these two different populations in the alpha abundance and metallicity plots. So these two actually separate beautifully, as we see the kicked out stars locate more towards the top right panel of this plot, which means they are more metal rich. And alpha enhanced. So this can actually be expected from their very distinct formation mechanisms, because one formed inside the massive host, and the accreted one, they are very likely to form in those low mass systems. So here comes the summary. The very first point, the feedback events in the fire simulations often accelerate molecular clouds inside which those physical conditions are met to trigger the star formation, creating those outflows. And as you can see in the movie, it often occurs at early times, and those stars might even fall back by z equals 0 and contribute to the outer stellar halo region. And the second part, the fraction of the kicked out population, or the fraction of stars born within a galaxy, if you don't believe in our first point, is about 10 to 20% in the outer stellar halo. And the third point, there are properties that kicked out stars, or the star born inside a galaxy, tend to be more metal-rich and alpha-enhanced, but show no obvious signals of clumpiness or substructures. And the fourth point, if you believe that our first point is true, then the stellar halo today may contain stars born in the molecular outflows, which means maybe we can use it to constrain or test the outflow models in the near field. And that's it. Thank you.
Questions?
So Claire Dorman made some measurements in Andromeda, and her estimates of the kicked out fraction based on, she finds a population of stars that have an exponential profile, but they're very hot in terms of velocity dispersion. Her estimate is about 15% for the population. 15% of the halo population appears to have this kind of kicked out character. So happy to chat with you about this.
No, we haven't. So we haven't checked about like the observations. Like since the current observation, they mainly focus on in the like the very there, because here what we are looking at is like really distant stellar halos, like outside, even outside 100 kiloparsec, which like most of the observations has not like observed that far. So that would be very interesting if you guys have found like in Andromeda, like this population is actually really important.
That's a statement about the inner halo, but we do go out to 200 kpc in Andromeda. So we do go out to the outer halo.
Hi, sorry, I might be getting confused here, but when you showed the phase space diagrams, yeah, so if the stars formed in the galactic, in the galaxy basically when they were passing near the pericenter, why are there kicked out stars in the infall stream? Like,
sorry, oops. Do you mean like
here?
Yeah. So we think it's because they got kicked out first.
Out,
and
like yeah, out of the halo?
It depends on how you define a halo. Like so far we are using, for example, the virial radius to define a halo, but we don't actually really know like how far is like the halo. And so here, what we believe is that the star got kicked out and then interact with, for example, the disk and the galaxy potential, and finally, after some time, it got deaccelerated and then will start to fall back and will form this kind of like falling back patterns in the phase space.
Okay, yeah, thanks.
More questions? Yeah. Let's thank again to our speaker.